Hi, I'm Francisco Guzman, and I'm going to talk about multi-state configurations of fuzzy dark matter. So this is the talk. So let me start describing the contents of this short talk. So I'm going to talk about what fuzzy dark matter is, some of the properties of this paradigm, and at some point we'll come up with a construction of multi-state configurations based on what I will say on simple stationary configurations. And we'll talk about stability information properties of these configurations, so as potential applications. So what is this fuzzy dark matter? So the origin of fuzzy dark matter actually comes from relativistic theories coupled to scalar fields. So in 2000, and this paper from 2000-2001 by Matos and Urena Lopez, so they, with the aim of studying a dark matter model that could explain the cutoff of power spectrum of cosmological perturbations. So they proposed the scalar field with this potential coupled to general relativity. And they found that there is one parameter that cuts off the power spectrum. This parameter would be the mass of the scalar field. So you can see this is a very general scalar field potential, but it contains actually the even powers of phi. So you have the first even power and the second, which is 5 to the 4th. This would be the free field case, and this would be the self-interaction contribution. So this parameter had to be very small, with masses of the scalar field of the order of 10 to the minus 23 electron volts. So from there is the name of ultralight scalar field or bosonic dark matter. So one of the properties of very light particles is that they have a very high temperature condensation, and if they are bosons, then there will be condensates at very early stages of the universe evolution. With a very small mass, also, you have a large de Broglie wavelength, which determines the range of interaction between particles, and eventually will determine the size of structures that these particles can build up. Actually, what happens is that what you need when you're trying to describe the nonlinear evolution of structures, say galactic or cluster scales, you will need not to deal with the relativistic theory, but you can actually use the low energy limit and the Wakefield limit of general relativity, ending up not with the Klein-Gordon-Einstein system originally in this theory, but with the Schrödinger-Poisson. So it happens that the Schrödinger-Poisson is a system that has some similarities with macroscopic systems. So for instance, this Schrödinger equation also is the same equation as the Gross-Pitayevsky equation for a Bose condensate at 0 temperature, which is a very idealized situation. But what happens in the system is that if we interpret this equation as the one ruling the dynamics of a Bose condensate, is that the potential trap, which is this V, is actually the solution of Poisson equation sourced by the density. If you interpret psi as a density, as the wave function, then you will have a density of probability. If you interpret this psi as the order parameter of the condensate gas, then this would be the density of mass of the gas. So the trap, the potential trap, would be sourced by the gravitational, by the gravitation due to the density of the gas. So this is also why it's called Bose condensate dark matter. So in the last years, in particular since 2014, some groups have actually solved this system of equations, Schrödinger-Poisson or Gross-Pitayevsky-Poisson system, even to simulate the structure formation in the universe, to compare with the CDM simulation. So what you have here is actually a real simulation from that year. And what the authors found, it was a really interesting property. This is another group that carried out structure formation simulations, is that the structures collapse in density in configurations which have this sort of density profile, which is called soliton density profile. I will describe later why. So this is actually an approximate density profile of what is known as equilibrium configurations of the Schrödinger-Poisson system. If you assume that psi has this harmonic time dependence, then and assume that the system has spherical symmetry, you will notice that you have stationary solutions, because you can see that psi squared here will be time independent due to this time dependence. And then you will have an independent, time independent potential. And this expression for psi also reduces Schrödinger equation to the stationary Schrödinger equation. Then you will, in principle, obtain stationary configurations. This can be obtained, as usual, defining a Sturm-Liouville problem with boundary conditions for psi and b at the origin, and for psi and b at a certain finite but far distance. So this would be the numerical domain, this would be the coordinate r, and you will end up constructing configurations with this profile for psi. And this would be psi. Okay? So different curves for different values of this self-interaction coefficient. Actually, this self-interaction coefficient is really labeled to be lambda capital. So for different lambda, you have either fatter or thinner configurations. And you obtain a family of solutions depending on the value of the central wave function. So you can construct a family of solutions. What we showed later on is that the solutions are really stable. And not only stable, but also attractor solutions in time. In fact, you see here, this would be the core of all the equilibrium configurations, depending on the value of the central density. And you can start with various initial density profiles. They will end up, asymptotically in time, being attracted by this core. We also showed that these configurations are stable against very general perturbations. In this case, we are using a very general perturbation and show that the configuration is really stable. Of course, these configurations have been used with many purposes. One of them is to fit galactic rotation curves. But of course, as this profile seems to be very universal, and you see galaxies with different density profiles, then probably you can do something to rescue this model from failing and having all the galaxies the same type of rotation curves. And what we did in this case was to add some rotation to the equilibrium configuration. And we ended up with a very wide class of rotation curves that could eventually help to fit rotation curves, as we did in a paper in 2015. Also, these configurations oscillate with certain frequencies. So we have found the spectrum of oscillation. So in principle, if these configurations exist, they should have a very clear response to perturbations. And we have found the different frequencies in different modes of oscillation. So it was actually from the last year, this paper last year. Also, there have been carried out experiments with collisions of these configurations in particular. And with matter or without matter, just to see whether this luminous matter can be tracer for dark matter, this fuzzy dark matter. And there are many parameters in a collision, so you can have many different situations. So for instance, here you can see this movie, you have a collision of two of these configurations with the same mass, or you can have collisions between configurations with different masses, and you can see, like in the plot on the right, whether or not the system is being virialized or not. So you can study very interesting properties of the system. In fact, you can show that the final configuration is rotating and has a profile that can be fitted with this density function. This is the case of psi being a single state. So let's think about what would happen if we think that the configurations can be in more than one state. So for that, you need to solve not one Schrödinger equation coupled to Poisson equation, but you can have many Schrödinger equations, each of them with different quantum numbers NLM, and that share a gravitational potential B sourced by the densities of each of these states. So you propose a general wave function of this form with, again, harmonic time dependency, and with the base of spherical harmonics. So you can actually solve this system of equations also using Sturm-Liouville setup. And what we have done so far is to construct mixed configurations with the 100 state and the 210 and the 211 configurations. Why? Well, the reason is that there is a motivation to study this. So there is an interesting problem called the BPO's problem, which consists in that satellite galaxies of some major galaxies like Andromeda, the Milky Way itself, and Centaurus A have galaxies traveling around, but in very strange trajectories, nearly in planes which are almost perpendicular to the galactic plane, and that cannot be explained. So what we did in principle is to use one of our configurations, for instance here the 100210, and launch a bundle of test particles and see how they distribute. So you can see here the position of particles after an asymptotic time, how they approach, they accommodate along the poles. So these are particles that are beyond 50 kiloparsecs from the origin, for instance. So, and this is a paper that has been already published in the archive and is submitted for publication still. So, but this is kind of a wishful thinking unless we show that these configurations can be formed, or at least they are stable. So here we show that they actually are stable. So we put one of these mixed state configurations, solve the in full 3D the Grosspitaevsky-Poisson system, evolve it, see that it's not destroyed, and moreover, we track the Fourier transform of the wave function and see that the frequencies correspond to the frequencies or the eigenfrequencies in the time dependence on these ansatz. So we show they are stable, we show they oscillate with the correct frequency, etc. They don't get destroyed. But moreover, we did some experiments just by solving the two states Schrödinger equations coupled through the Poisson equation for the green and for the purple configurations. We collide them, and what we find is actually that the one with the smaller mass splits like if it were a 2-1-0 mode. Look at this. This is not a coincidence. This is a generic behavior, and we are working on it. This is a case of a mass ratio of 0.9, for instance, with a given head-on momentum parameter. So we actually showed that this type of configurations can exist. And okay, so this is the state of the art. This is the status. We are able to construct these mixed state configurations with 100, 210, and 211 states. We have shown they are stable or long-lived, at least, within a range of parameters and mass ratios between states. And we also showed that numerically these configurations can be formed. And moreover, we have shown that they can be applicable. So for instance, for the BPO's problem. Hopefully, if we are lucky, we will present a model which is very kind, very cute, and that has solutions which are just a result of the theory that could explain this behavior at galactic level. Okay, thank you very much. This is my talk, and this is my email address, just in case you have any questions. Thank you very much.